Okay. Well, first of all, thank you very much for inviting me today. It's a pleasure to be here. I was very happy when Heidi reached out and proposed me to participate and giving a talk to all of you. My name is Joan. I'm a postdoctoral fellow at the University of Victoria, and I'm a marine ecology, working basically with the ecology of deep sea and specifically with hydrothermal vent communities, with our communities too, but I have been working quite a bit with these communities since my PhD. So in today's talk, I would like to, wait, okay, here we go. So in today's talk, I would like to talk about the ecology of hydrothermal vent communities, also about exploration of these communities, why exploration is still important in this field of research. And I would like to finish with some work that I have been doing here in Victoria, together with Amanda Bates and other collaborators, about the functional diversity of these systems. I'm going to talk about what is this term, functional diversity. Okay, before we get into hydrothermal vents, I think it's important in order to understand the uniqueness of these systems to understand how terrestrial system works as a comparison. So the vast majority of systems that we are used to it are based on photosynthesis. So basically, plants use the energy of the sun and water and some compounds to do energy and then create organic matter. After that, invertebrates and other animals can eat directly the plants or eat other animals, and then that's how ecosystems are created. So basically, we have these primary producers that use the energy of light. When we go to the deep sea, things look kind of like this picture that I'm showing here. The very first thing that you can see is that the density of animals is rather low, and it lacks the structural complexity that we observe, for instance, in forests or other ecosystems in the terrestrial environment. So let me, before I explain why it's so, define a bit the deep sea and how this environment is, so you will better understand. So the deep sea is the largest environment on Earth, and it's defined as the environment below 200 meters depth. And it goes all the way down until the Mariana Trench, which is the deepest point on Earth, 11,000 meters. It is an environment that has very high pressures on average because it has on average 4,000 meters depth. And it's also a very, very cold environment, on average 4 degrees. And so in this environment, photosynthetic production is either not possible or very limited. And this is because photosynthetic production made by phytoplankton, basically, is produced on the first 200 meters depth. This layer of water is the one that is impacted by the sun. Deeper than that, the sun cannot penetrate. Sunlight cannot penetrate, so this photosynthesis is not supported. So just to give you an idea of all productivity in this 200 meters depth, only 0.5 or up to 2% reach depths of 2,000 meters. So basically, the deep sea is very, very food limited. There is no production because light do not penetrate. Photosynthetic organisms cannot produce organic matter. So that's why we have these low abundances and low biomass systems in general, because there are some exceptions. And today, we are going to talk about one of those exceptions, hydrothermal vents. So hydrothermal vents looks like that. Those are basically hot springs, very deep in the ocean, where these kind of plumes of chemical compounds are being expelled. And it also has, as you can see, all these high densities of animals. very weird animals. We are going to talk about them in a second. But this is how hydrothermal vents look in the deep sea. Okay. So just to give you an idea, everything that I will show you today are communities or hydrothermal vents that are located in between 1,000 meters depth all the way down until 5,000 meters depth. There are hydrothermal vents that are found deeper and also shallower, but the ones that I'm going to talk today are more or less in this range. So just to give you an idea. Okay, so what are hydrothermal vents? How are they formed and where are they located? It's going to start for the last question. So hydrothermal vents are located all around the world, but very specifically along the tectonic plate boundaries in our oceans. So you can see here these black lines and all these dots. Each of these dots is a hydrothermal vent. And so it clearly shows that they are basically found in these boundaries of tectonic plates. And the reason why are found in these regions is because those places are tectonically very active, but also volcanically very active. And so in these regions, seawater percolates through the ocean crust and then starts reacting with the rocks. And by doing so, hydrothermal vent fluid is created, which is basically a fluid very rich in some chemicals that gets very warm and then is expelled all the way back to the seafloor. And it's being expelled at very, very high temperatures. So up to 350 degrees Celsius. The animals that I will show you today and the communities do not live in direct contact with these super hot fluids. They live more in the areas surrounding where temperatures range between 2 and 60 degrees Celsius. But in any case, these very warm fluids all of a sudden react with the very cold seawater that has now a completely different chemistry. And because they are very rich in metals, they precipitate and they form these chimneys, the hydrothermal vent chimneys that I'm sure that many of you have already seen. And again, because these fluids are very rich in some metals, they react, they precipitate, and they create these chimneys. So animals are distributed within these chimneys, mainly in the bases, but also all around. Okay, but as I was telling you, these fluids are very high temperature fluids, especially considering that the deep sea is very cold, and are also very charged in chemicals, many of them toxic for life. So how is life sustained in these environments? So it turns out that these environments are very rich in bacteria, and some of these bacteria are able to use these chemical compounds that are being expelled with the fluids and use them to produce energy. So if in photosynthesis we were talking about light, taking light to produce energy, here this bacteria is able to take the chemical energy of these compounds to produce energy. And that's a process that it's called chemiosynthesis. So rather than photosynthesis, here we have chemiosynthesis. Well, this meeting log, allow or not allow? Okay, enable. Allow. Okay, sorry for that. Okay, so not only bacteria is able to produce energy, but some animals have symbiotic relationships. They have evolved a relationship with these bacteria in order to produce energy. So we are talking here about very specialized animals, very endemic. And by endemic, I mean animals that are only found in these environments. I'm going to talk a bit more in detail. So probably the most iconic example of all these animals that present symbiosis with bacteria is the giant tubworm, also known as Riftia pachyptila, is the technical scientific name. And so this animal do not have a digestive system, it's gutless. But instead, he has a symbiotic relationship with bacteria. Bacteria are found inside the tubworm in a very specialized organ that it's called trophosome. And this worm has this structure in red here called the plume, which basically is a structure that allows the worm to take several chemicals, including oxygen. These chemicals are delivered to the bacteria here, and these bacteria then do chemiosynthesis and provide the worm with the nutrients necessary to live and grow. So that's the way these animals are sustained in these very special places. What's that?
How big are they?
Well, these worms can be quite large, in between 1.5 and 2 meters, so taller than I. Not all of them, some of them, but yeah, those are animals that grow relatively fast. Okay, so yeah, we are talking here about very, very specialized animals only found at hydrothermal vents, and they are also what we call ecosystem engineers. Ecosystem engineer is a term that is used to characterize those species that are able to change the environment, to engineer the environment. And they do so because in those places, all the tubes of these very dense assemblages of worms provide habitat to other animals, and also because they are all the time obtaining these chemicals from the environment, they are making this environment better for other species that might be not that tolerant to these toxic environments. So, answering the questions of why these communities are able to support such a dense assemblages of fauna in the food-deprived deep sea, well, we now know that the production from chemiosynthesis plus the role of these ecosystems engineer favors the establishment of smaller fauna that is not necessarily chemiosymbiotic. Those smaller fauna that colonize all these environments do not necessarily have this symbiotic relationship with bacteria, but they feed on bacteria or other animals. And so this is the way that these super high dense and biomass-rich communities are formed in the deep sea. Okay. Okay, and how do these animals find all these communities down there in the deep sea? Here I show you again the map showing all the distribution of hydrothermal vents. And so here you can see a lot of points that are relatively close one to another, but that actually, all these points are actually separated by 10 to hundreds of kilometers. So the way these animals disperse through these communities is during the larvae stage. So basically, adults of animals produce a considerable amount of larvae that are being released on the water column, and then these larvae, using different currents, disperse until they find another hydrothermal vent, and then they'll settle and they start a new community there. So that's the way these animals disperse. Okay, and so these animals are very good dispersers, and usually each ocean or parts of oceans have very characteristic communities that are formed by animals that only occur there. So here I'm showing you the main communities that are formed in the world's ocean. And so as you can see, the East Pacific here has its own suite of fauna. Here in front of Vancouver Island, we have also another one in the Atlantic, in the Arctic, the Mont Ridge, also in the Southwest and West Pacific in general, we have several ones, Indian Ocean and East Scotia Ridge here in the Antarctica. All of these regions present very different communities. And I will now, just to give you an idea of how special the animals that inhabit these different systems are, I'm gonna do a small tour just to highlight some. Okay, so we are now here in the East Pacific rise, in the East Pacific, sorry, where we have these communities that are mainly or visually dominated by the giant tubworm. This is the same tubworm that I used before to explain the chemiosymbiotic relationship. So you are already familiar. Yeah, it has symbiotic bacteria in this very special organ, the trophosome. Here you have like 1.5, 2 meters length, very big, and a very iconic animal. If we go in the Atlantic, what we observe is that communities are usually dominated either by shrimps or mussels, or shrimps and mussels. And both of them present symbiotic relationship with bacteria. Mussels usually belong to the genus Basimodiolus, whereas the most iconic shrimp in the Atlantic, it's called Remicaris exoculata. And as you can see, is a blind shrimp. It does not have any kind of eye, but instead it has this very large anterior part or head, if you want, and that's because it has a very well-developed gills. So it can capture a lot of oxygen and it can capture the chemicals necessary to feed the bacteria it has inside. Let's go now to one of my favorites, the Indian Ocean. You can see these very beautiful vent communities. And in some places, like here, here, and here, all of these are gastropods, snails. And it's a very specific species of a snail that it's called the pangolin snail, or scalyfoot snail. It changes depending on the scientific name is Chrysomalion squamiferum. And again, this species has bacteria in the gills. And the most characteristic feature of this species is that it managed to put iron on the shell and on the scales here on the foot. So basically all this black color here that you're seeing in the shell and the scales here in the foot is basically iron. This is one classical example of how these animals evolve crazy adaptations to this environment. So by putting this iron, this mineral into its body, it makes basically a very well-protected animal. And this is something that even the United States Army has studied in order to develop bulletproof vests and this kind of technology. So just to give you an example on how these animals can inspire technological developments. Okay, those are the hydrothermal vents that we find in the Antarctic Ocean. And as you can see, they are all covered by white crabs. And these crabs are called the Yeti crabs. The scientific name is Kiwa tyleri. And as you can see, they are called Yeti because they have these very hairy arms. And in these arms, or using these hairy arms, what they do is to farm bacteria. They farm the bacteria there and then they eat it. So in this case, it's not a symbiosis like the giant tubworm that the bacteria was inside. In this case, the symbiosis is outside. But in any case, it's a similar process by which this animal farms all these bacteria in the arms and then eat it. And finally, just I'm gonna finish here the quick round all around the world. Those are the hydrothermal vents that we have just in front of the island of Vancouver. Those are hydrothermal vents that the dominant species, it's also a tube worm. In this case, is a relative of Rhyptia pachyptila, a bit more to the south. It's a smaller species, it's not as big, but it's pretty similar in the way it lives and functions. And well, the scientific name is Lamellibrachia barhami. So those are the animals you could observe if you go some kilometers offshore and then look at the vents in front of Vancouver Island. Okay, well, I think that I convinced you that these communities are wonders of nature. They have all these amazing animals with these crazy adaptations and life styles. And in fact, these communities have been thought traditionally as very remote environments because they are deep in the deep sea, relatively untouched and pristine. No one ever did anything. Humans are not there. So scientists were very, not really concerned. But that has changed in the last decades. So eventually, these habitats lost the activity and became inactive. And so when they became inactive, they cannot anymore support chemiosynthesis because fluids are not being expelled. So animals cannot do chemiosynthesis, but they left these enormous metallic deposits. If you remember at the beginning of my presentation, I was telling you how the chimneys are formed and that they precipitate because of metals. So those in the end are gigantic deposits of metals in the ocean. And nowadays, if something, humans really are looking for minerals because basically everything works with electricity, including the cars right now. And so we need batteries and minerals, some of them found in these deposits. And so deep sea mining is now a serious threat for these systems. Again, it's true that they are targeting the inactive vents, but one of the issues with the inactive vents is that we know that some of them, after some time of inactivity, can start having activity again. And so that's one of the issues. The other issue, and I will be more specific in a minute, is that they can impact the active communities by altering the environment of the whole area. So yeah, this is just a conceptual diagram. Just for your information, hydrothermal vents are not the only environment in the deep ocean that is being targeted by deep sea mining. There are others, including abyssal plains, which are very rich in nodules, polymetallic nodules, but also the top of some seamounts that are very rich in cobalt crust. But in any way, what I'm trying to highlight here is that it's an emerging industry that we do not really understand how it's going to affect the deep sea. But we suspect, and we have good reasons for it, that it could radically change the environment. And so in the case of hydrothermal vents, the main impacts will be the removal of the habitat. As I was saying, also the alteration of the deep sea environment. As I told you before, the animals that live in these environments use the water currents to disperse. If you change the environment and you alter the quality of the water, some of these larvae might not survive and so never reach other hydrothermal vents. So we now have an urgency to understand these habitats as a scientist and all of us as a society. Okay, and here is when I'm gonna focus more on my research here at UVic, and I'm gonna give you two examples, one based on an oceanographic cruise based on exploration. We went to the Atlantic Ocean to explore some areas. The second one, I will focus more on the functional diversity of hydrothermal vents worldwide. So one of the main questions, if we are gonna go and exploit these systems for minerals, the very first question that you have to ask is, do we have a good understanding on what is there? Because if you don't know what is there, you cannot protect it, you cannot manage it. So that's why it's still important to do ocean exploration, because we still have a limited understanding of the deep sea and specifically of hydrothermal vents. So 1 year ago, I did a cruise with a multidisciplinary team, including people from NOAA in the United States, and we used the Smith Ocean Institute facilities to go to the Mid-Atlantic Ridge and do some exploration. So we used this fantastic research vessel called Falcon 2, that among other cutting edge and first class facilities, it has a remote operate vehicle that it's called Sebastian. This is basically a robot that you can send down there. It's connected to the ship. And as if it was a video game, you have a bunch of screens and you can go with this robot and collect samples and explore and do some very cool science. So we use that to, as I was saying, explore the middle of the Atlantic. And so here, this small green part here, that's Portugal. This here is Africa. And so we explore these 500 kilometers of the ridge, specifically 3 different points. The first point in the south called Puy de Fos, that's a French name. The second point called Imark, and the third point called Cluster 2. And in these 3 locations, we already had evidence, there was evidence that hydrothermal vents occur, but they were never seen before. They were never discovered. We knew it because the chemistry of the water suggests that there were some hydrothermal plumes here and there, but we never observed it. So our goal was to find the hydrothermal vents in these 3 places. And we find it. So now I'm gonna show you what we observed when we went down there with the robot. And just to, okay, here we go. So just to keep in mind, remember that when I was doing this tour all around the world, I told to you that in the Atlantic, usually we found a lot of shrimps and mussels. So here is what we found when we were diving at Puy de Fos. So the first thing that we observed was these assemblages of fish. This is a species that is relatively well known. We know which species, but never has been before observed in these super dense clusters of fish around hydrothermal vents. So they are there hanging, probably enjoying that the water is warmer there. We don't know yet, but still that was something surprise. We were not expecting to find such abundance of fish just or in these hydrothermal vents. You can see here, those are the shrimps that I was talking, doing these huge swarms. That is more like kind of what we would expect. But you can see also that there are some anemones here, some crabs here and there, more anemones. So that is basically what you observe from this robot. So there's a close-up, so much shrimps, some fish here hanging. Like eels? Yeah, they are called eels. Yeah, the generic name. They are not related with the eels that we are more used to it, the ones that are on rivers and these things, but yeah. How tall is this? Oh, these chimneys really change. This one in particular was about 14 meters. from the base to the top. But for instance, the ones you have here in front of Vancouver Island, those can be much bigger than that. It really depends on a bit the geology and the properties of the minerals. But yes, usually there are clusters of these chimneys. Yeah.
So each shrimp would be how long?
This shrimp is something about, I would say, 6-7 centimeters, more or less. Yeah. And we found mussels at Puy de Fos on the base of these chimneys. So this is a picture of how it looks, these mussels all together there. So I would say that, yes, it was surprising to see all these fish and it's very interesting. But overall, these are the communities that we were expecting to find in the Atlantic. Okay. Let's go now to Imark, the second site that we explored. So this is what we found. This is the base of a chimney, also about 14 meters tall. And as you can see, it was full of anemones. Some hydrothermal vents in the Atlantic have these kind of fields of anemones. But what we were not expecting is, as you will see now, that these anemones basically goes from the base of the chimney all the way up until you find the fluids where the shrimps and mussels would be expected. We found the shrimps, yes, but basically this carpet of anemone was everywhere, dominating. Some point, I think that the ROV switch on the light, and then you will see even better how dense this carpet of anemones was. So very beautiful images, but very confusing for us because we were not expecting to find such density of anemones in this hydrothermal vent.
So are those currents that are dragging these things around? It looks like this quite strong current. Is that created by the hydrothermal vent?
Partly, yes. I mean, those are very rough terrains that enhance deep sea currents all of a sudden, plus all the hydrothermal activity. Here we go. You can see how covered of anemones was all the hydrothermal vent. A beautiful sight, but again, very confusing for us because we were not expecting to find such communities. Okay, let's gonna go to the last site. This is the last site that we visit. And again, we were expecting mussels and shrimps. And we found some shrimps, as you can see here. But what we also found was extremely high density of gastropods, a species that was previously known, but it was never observed in such density. It was so dense that even the fish was on the top of these gastropods. I can tell if they are happy or not, but yeah. Yeah, that's the advantage of doing this kind of research nowadays is that these robots have 4K cameras, a bunch of sensors, so it's much easier and you can obtain these images. This, just to give you an idea, this one specifically was at 4,000 meters depth. So that's very deep.
So that big, whatever, how long would that be?
The snail?
Not the snail.
Oh, the eel. Difficult to tell. I would say like about 30 centimeters, more or less.
Okay.
Yeah, like.
The snails are just
Yeah, the snails are not that big. Yeah, yeah.
What are the snails feeding on?
That's a good question. We don't know. We don't know what they are eating. Those snails are described as carnivorous, but it doesn't look to me that there is a lot to eat, unless they are not, and they cannot feed on bacteria because the mouth apparatus they have.
You wouldn't mind repeating this into the microphone, but someone's asking about the white beneath snails, so I don't think they realize that's part of the body.
Oh yeah, that's the foot of the gastropod. This white part is just that it's a white foot, very extended. So yeah, that's the foot of the gastropod basically. You're welcome. Okay, so coming a bit back to the question. I don't know if I can take this here. Okay. So as I was telling you, this is a picture that we were expecting these huge swarms of shrimps. But instead we found that the three sites that we visit were presenting very different communities. So why these communities look so different? This is something that we do not know. We are now working, analyzing all the data of the cruise and trying to figure out why is so. But the main point of all these that I just show you relates to the question on, do we have a good idea of what's down there? Well, still 2024, we are going down there and finding things that we do not understand. So this kind of highlights the urgency to better understand these habitats if the industry wants to exploit them. Okay, we'll talk now the last part of this presentation, which is about the functional diversity of deep-sea hydrothermal vents. This is a work that I did here at UBIC as well, just when I arrived in 2022, and where we basically analyzed the functional diversity worldwide, and is the presentation that I gave in the Congress that Heidi was talking before. So can I minimize that somehow? Maybe I can put it down here so the people here in the auditorium can see it better. Okay, it works. So when we talk about species diversity, we are usually talking about species itself. How many species are there? So the species richness, the number of species, or metrics that use the number of species and their abundance. But when we talk about functional diversity, we are not looking directly to species, but we are looking to the diversity of traits or their characteristics. So, for instance, the mobility of the species, if they are sessile, slow, fast, the size of the species, if they are small or big, or even the feeding mode, if they are symbiotic, if they are predators, and so on and so forth. So all this diversity of traits is what constitute what we call the functional diversity. And the functional diversity has several advantages compared to the species diversity. One of them is that it gives us a better understanding of how the ecosystem works. So what I did at UBIC is to analyze 511 species from 11 regions all around the world and derive the functional traits and analyze the functional diversity of these communities. And then we generate a bunch of metrics related with the functional diversity. One of the ones that we were more interested in is what we call the functional vulnerability. So the functional vulnerability, it's a metric that relates with the functional insurance against species loss. And let me explain that. If you have a species that is functionally unique, that means there is no other species that is similar to this species is performing a unique role. Okay. If you lose this species, then you are losing a species that is unique. And so you are going to lose some functions that cannot be done by other species. Instead, if you are losing a species that, let's say, there are 3 other species that are very similar or doing exactly the same, if we lose one of these 3 species, we still have 2 that somehow can compensate. And so we are not losing that functioning. So that's why this concept of functional insurance against species loss. So we analyzed this metric for all the different regions of hydrothermal vents in the deep sea. And for our surprise, what we found is that basically all the different regions have 50% or more species that are functionally unique. So they are exclusively doing some roles in the community, and there are no species that can replace them. And so basically, we found a very high functional vulnerability in all this. And that's very important and concerning at the same time, because we know that deep sea mining could negatively affect these habitats. It's very likely that very quickly species are going to be lost. And based on that result that I'm showing here, it's very likely that many functionally unique species are going to disappear, and that could impact the way this system functions. So very concerning results. So until here, my talk, the main conclusions are that hydrothermal vents are wonders of nature, very special habitats with very special animals. But the deep sea mining and other emerging industries represent a serious threat to these systems. Exploration is still needed. Those systems in the deep sea is not like other systems on land that we know already where they are and we can use satellites. We still have to use ships and robots to go down there and find where these systems are. And even when we do that, as the example that I showed to you, we found some very surprising results that we still do not really understand. And finally, as I just showed it to you, hydrothermal vents are functionally vulnerable. So we have to take a lot of precaution before we exploit commercially these habitats. With that, I would like to thank you very much for the ones that are here in person and also all people on Zoom. And I would like to thank also, of course, the University of Victoria for hosting me, and my supervisor, Amanda Bates, and my collaborators, Abby Chapman and Verena Tunnicliffe. And also, of course, the Smith Ocean Institute and the crew and scientific team of our cruise. Thank you very much. Oh, I see there are a lot of comments.
It's mostly me, don't worry.
Oh,
Yeah. Thank you so much, Juan. That was incredible. Excellent talk. For those of you online, if you want to speak, do you want to actually open up just the talking there and then we can see their faces a bit more? Sorry, top right corner. I can do it if you need to.
yeah, maybe. This one here?
Yeah. If you want to turn your camera on and ask a question, you're welcome to raise your hand. If not, feel free to put questions in the chat and then I'll read them out on their behalf. But since we have an in-audience today, let's go to the in-audience first.
So I'm wondering about the deep sea mining, another stupid thing that humans do. Like, oh my God, well, we see that machine, like, I found that very scary.
Right.
How developed is this at the moment? Like, there are a lot of bears in mining?
So for our online audience who couldn't hear that, we had an audience member asking about deep sea mining and kind of wondering how far along is this in its process, that sort of thing.
Yeah, so as I told you before, there are several environments that are being targeted in the mining industry. Hydrothermal vents and seamounts are the more difficult ones to exploit because the terrain is very rough, so the machines are basically not ready. It's a matter of time that the industry develop this technology. However, on the abyssal plains that are full of nodules, nodules are potato-sized rocks of metal that are put here and there in a very smooth and gentle terrain of mud. And so those are very easy to retrieve with machines. And so in this environment, in abyssal plains, for nodules, the technology is much more ready. And that could be a reality in about 2 years. It's actually, technology is not anymore limiting in this environment. What is limiting the exploration is all the conversations that are going on between countries to set a series of rules and terms. And so countries are negotiating if it's worth or not exploit these systems. But in terms of technology for abyssal plain, it's not anymore a limiting factor. The technology is there, it could be done, and yeah. I was talking before, and one of the main limiting factors right now is the market of metals itself, because it's so fluctuating that it's still kind of risky for industries to invest. But in terms of technology, for the abyssal plain, it's feasible.
Thank you, Joan. And yeah, I believe they did their first test at sea in the past year, and it wasn't looking great from an environmentalist point of view. Let's just put it that way. Getting lots of great feedback about what a fantastic talk.
Well,
thank you so much. Dr. Ryan, can you turn down your camera? Would you like to ask a question first?
Thank you. Oh, very, very interesting. Just a couple of short questions. I noticed that the fish, I don't know, zeracids or whatever they are, they still have seemingly well-developed eyes. Like, what's the issue here from your perspective of why there still should be a retina and light sensitivity down there?
Yeah, that's a good question. And honestly, I don't know. But so not everything in the deep sea has lost organs like eyes. Sometimes they lost it because there's no light to see there. But they sometimes preserve. There is a lot of bioluminescence in the deep sea as well. So sometimes could be interesting to detect prey here and there that might use bioluminescence. I'm not sure it's the case of these fish. These fish usually we believe this fish eats shrimps, the shrimps of these very dense swarms of shrimps. So that would be the main prey. But yeah, I cannot really tell you why it still have these super well-developed eyes. But yeah.
All right, okay. Yeah, thank you. So the second question is, a lot of the, I guess it's mesopelagic or maybe bathypelagic fishes and invertebrates are red. And I didn't see any redness. So on the higher vents, does red ever come into the pigmentation of these organisms that live in more shallower vents?
Yeah, red is a color that is, as you said, is very common in the column, in the water column. And I guess that it has to be related with the properties of light itself. And but at hydrothermal vents, animals tend to be white or red. But when they are red, it's because they have a lot of pigments on the blood, so they can obtain a lot of more efficiently the oxygen, because at some parts in these environments is so heavy in chemistry that oxygen is limited somehow because it reacts, and also because the fluid itself is anoxic. So the reddish colors in hydrothermal vents animals usually are because the hemoglobin and all these pigments, rather than camouflage or other.
Yeah. Okay. Yeah. Thank you. Thank you.
You're welcome.
I closed the app on my phone, so I'm gonna go here.
Yeah, go ahead.
The chats disappear if you reopen the app. Let's start here. Are black smokers found? Do you mind reading out loud and then just?
Are black smokers found only in certain areas? Anita Claudia Roberts' daughter, Lewis. Yeah, well, black smokers, what we specifically call black smokers are the chimneys that are venting super warm fluids. So there are smaller chimneys and areas around that are venting not that warm fluid of around 260 degrees. The ones that are venting very warm fluids are those that you can see the black smoke coming out, and those are what we call black smokers. These black smokers are very often found in all hydrothermal vent systems. And as I said before, like these systems are usually found in tectonic plate boundaries, where the water can percolate through the ocean crust and react with the rocks, and then being expelled back to the seafloor and precipitate. But yeah, aside of these places, no, there are no other places where you can find black smokers.
I'm just gonna stop the screen share. if
Oh,
you haven't
yeah,
already.
sure. Sorry.
No, that's okay. Go big. I think I've stopped sharing now.
Yeah,
So, okay.
I just stop sharing, so
Okay.
hopefully you can see me better.
Is there any way to age the communities?
It's years old. Okay, yeah, so at the beginning, when these communities were discovered 40, 50 years ago already, people thought those animals were kind of fossil animals, animals that start way before, and they kind of like stay in hydrothermal vents without changing. We now know that these animals are not that old, and hydrothermal vents have been colonized several times. So the animals that we observe today, they are not necessarily super old animals. And this is in terms of evolution, if you want. In terms of ecology, depending on where you are, hydrothermal vents last more or less. So some communities in the Pacific can last for less than 10 years until they become inactive, or until there is a volcanic eruption that destroys them completely and they start again, or the ones in the Atlantic that have been active for some of them thousands of years, constantly or almost constantly supporting these communities.
Anyone in the audience? You haven't asked one yet? Would you like to go?
Yes, a couple of questions. Thank you first of all for a wonderful presentation.
My pleasure.
Very good. Which international organizations have the lead responsibility for providing adequate resource management over these sites?
Right.
If you wouldn't mind repeating that. Okay.
Yeah.
So for those of you online, it was a question about, so who is basically making these decisions about the deep sea, about mining in areas that are beyond like countries' jurisdictions?
So there is an organization that it's called the International Seabed Authority, the ISA. It's based in Jamaica, and they are having recurring meetings where they invite all countries. So that's the level of United Nations, and it's there where basically discuss all these issues. There are countries that advocate for starting the mining. There are countries that do not want that happen yet, and there are countries that are there observing. There is a bunch of groups like Greenpeace or DOZI, these kind of groups that go there also, and they can express opinions and ask questions, provide information. So these are this kind of negotiation that takes a lot of time to reach an agreement or a consensus, and there are a lot of filters and meetings. At least I would say there are 2-3 meetings per year in Jamaica where all these things are being discussed. And also they target sometimes specific areas of the ocean. There are areas that are more advanced than others.
Just because someone asked a question, it's not the United Nations though.
Oh,
If you can say that.
What, sorry?
It's not the United Nations that's leading it. It's something different.
Oh, well, it's the International Seabed Authority, yeah.
Yeah. Did you have a follow-up?
Yes. This is going to be about reference to Juan Puka as one of your sites. Could you tell us more or less where that is?
Yeah, so, well, basically, it's, so here we are on the island. If you go straight offshore, as if you were going to Japan or Hawaii. After, I wouldn't be able to give you an exact location in terms of kilometers, but after, well, you maybe know better than I actually, because you go there.
Yeah, it does vary depending where you go on the bridge,
Here we go.
but oh, sorry.
Yeah, so the question is, where is the Juan de Fuca Ridge? So just off the coast of Vancouver Island, we actually basically have the world's smallest tectonic plate, which is really cool. And that's where a lot of this activity tends to happen. And so it depends what site you're going to, but it's about 60 to 100 kilometers offshore, depending how you want to measure that. But what's really cool is we can reach it within a day or two. And then also institutions like Ocean Networks Canada, they actually have cabled observatories to the edge of it. So it's in our waters and is managed by Fisheries and Oceans Canada, and working with First Nations to establish a larger marine protected area that will encompass the whole ridge. And right now there's a site that's a marine protected area called the Endeavour Hydrothermal Vents. Super cool. They were discovered here by Dr. Verena Tunnicliffe. And yeah, just have been an incredible source of knowledge for the world globally about these really cool sites. So very neat that it's like right in our backyard.
Yep.
Yeah.
It was the first mine protected area
Yeah.
in Canada.
The first marine protected area in Canada was this very cool deep sea site, hydrothermally venting. And I like that it's a deep sea site for the first marine protected area in all of Canada.
Yep.
And yeah, a lot of amazing research has come out of it. And then just to follow up, someone asked basically, is the International Seabed Authority like associated with United Nations? No, it's not. It is a very interesting organization that I encourage people to look into and form their own opinions on, but it is largely run by countries who have a vested interest in the deep sea mining. So it's, yeah, there's lots going on there.
It's a pity that Verena Tunnicliffe is not here.
I think she's not.
It's online. Okay, then Verena can talk a lot about that. Verena is an emeritus professor at UBIC, and she's the one to ask all these questions. Like,
Yeah, let's turn her mic on.
yeah.
Well, I'm not too sure how to word that question, but it's surprising to see like a lot of the species are from phyla that we found also at other like a shallower depth. Clams and
Right.
snails and
Right.
anemones and shrimp, and so how do we? I would have expected like creatures that would be completely like a new phyla.
Right.
Are these phyla that don't exist only around?
No. So the question is that although these species are have these adaptations, they are clams, mussels, shrimps, and so they are not that different to other shallow water habitats. And why there are no new phylums, for instance, or very new groups of species living there. And the reason why I think that, well, my answer would be, I think that there are groups of animals that are evolutionarily very flexible and they can adapt to new environments. So if you think from the perspective of the deep sea, when I start my presentation, I put a lot of emphasis in saying like, it's very poor in food. So all animals have to be adapted to eat to this food scarcity somehow. And all of a sudden you have all these bacteria that is able to produce energy. And so if you evolve in having these symbionts, or you evolve to tolerate the conditions in these habitats, all of a sudden you are in an oasis of food in a desert where there's nothing. So that would be probably one of the reasons. The evolution of animals in these communities, targeting the exploitation of these food sources. So that could explain why instead of appearing a new phylum, for instance, other species in the deep sea have evolved to exploit these habitats.
But how did like a snail, how would it have come down to that?
Okay, yeah. So the follow-up question is like how can, for instance, a snail reach these habitats? So there is a very interesting theory. These are one of the habitats that support chemiosynthesis. There are other ones, and one of these other ones are what we call organic falls, for instance. And that would include whale carcasses, whales that die in the surface ocean, then they sink. So those are huge animals that all of a sudden sink and reach the seafloor. When they start to decompose, the chemicals that they emit are relatively similar to the chemicals that we found at hydrothermal vents. So this provides what we call stepping stones. So animals can little by little reach the very deep sea using these whale carcasses. It somehow logs of sunken wood, for instance, like trees and these things can also produce these kind of organic fall communities. So we know there are evolutionary mechanisms that allow these animals to jump from one community to the other, evolving until they reach hydrothermal vents. So that would be a mechanism.
Thank you. Yeah, I also just want to highlight that even though, yeah, you're seeing shrimp that look kind of like our shrimp, it's always so fascinating that they have such extreme adaptations to this extreme habitat.
Yeah.
And every single time we go down to the deep sea and we have the ability to collect and we bring things up to shore, we try to get taxonomists, so people who put names to species to look at them. Phil does this as his job. And like every time there's new species to science, it's incredible. And I can't tell you how weird it is to be down in the bottom of the ocean, be like, what is that? And so sometimes, even though we roughly know what it is, it looks so different. And an example is like, do you guys know what a ctenophore is? It's closely related to a jellyfish. It has little cones on the side of it that kind of wave in the water. Down in the deep sea, they've attached to the bottom, and then they send out these long tentacles that like string off, and it just looks like a gloop of jelly. And then all of a sudden, it just looks nothing like what you would see in the water column. So even though we have a rough idea, sometimes it's just so strange. Yeah. We have another question here in the audience.
Please.
I was wondering on the energy levels of these critters, and what is the water temperature at the thermal vents compared to, you said -4 is an average? Is it that cold at the vents, or with the hot water coming out around the vents within where these critters are growing? Is it substantially warmer so they don't have to use as much energy to survive? Because it takes a lot of energy in a cold environment to just live.
Yeah.
I'm wondering what that balance is.
Yeah.
So the question in the room was related to energy and the temperature of the water. So -4 degrees Celsius is kind of what is,
4 degrees.
or sorry, not -4, 4 degrees Celsius is what you're kind of getting as ambient. And then we are talking about the temperatures at the actual vents and how it affects the animals.
Yeah, so I would say that the temperature that the majority of animal lives is up to 60 degrees Celsius, something like that. That is where the majority, like the peaks of temperature. In average, probably we would be talking about 20, 30 degrees Celsius. Yeah, and then I'm not sure that the energy, so if we are mammals, right? So in cold temperatures, we need a lot of energy to keep our body warm, because our body has to be around 37 degrees Celsius, something like that. But that's not the case of invertebrates. Though the invertebrates in the deep sea, they do not need to be at higher temperatures at 4 degrees. They can be at 4 degrees. So that's not limiting in this world of invertebrates. Then, of course, the animals that lives in these warmer temperatures are more adapted to deal with the toxicity of the environment in terms of physiology, rather than temperature itself. What they do have is a lot of behavioral adaptations, because these hydrothermal vent fluids are very variable. So now are 20 degrees, but 2 seconds later could have a peak of 60. And you can see the shrimps that I showed to you. I don't have the video here, but you see some shrimps that have the antennae completely burned, because they were there and all of a sudden there is a peak of temperature and they got burned. And then all of a sudden you see like the shrimps going, doing a step back, and then they come in again. They kind of follow the chemicals. But yeah, I would say that temperature in this environment is not a concerning factor in terms of energy, and neither the cold temperatures.
Even for the fish, the eels?
For the fish, it could be more, but yeah, I wouldn't say that temperature is that much of a big deal. Yeah. Yeah, go ahead, please.
So does that mean that the warming of the ocean will not really have much effect on these ecosystems?
No.
Yeah, so the question was, will the warming of the oceans associated with climate change affect these deep sea habitats?
So one thing is these species that lives in these very special environments, fine for them. But then when you change the temperature of the whole ocean, especially in shallow waters, the most known example probably are corals. They have a symbiosis with algae. If it's too warm, they cannot maintain the symbiosis, so they become white, the bleaching events. That could be one. The other thing is that you start changing the chemical properties of the ocean. So a lot of animals, in order to disperse, need currents, and these currents are partially driven by temperature changes and these things. If you homogenize or warm the ocean, then these currents change, and then you start having a population of species that are not anymore connected because you have change. And so it's more these kind of effects you're having. So especially for, shallow and not in the deep sea, not hydrothermal vent species, having a warmer environment, yes, implies serious physiological consequences that can be fine until the population and ecosystem level.
And I apologize, I also study the deep sea, so I'll just add in quickly that here in the Pacific, we've had studies that one of the associated things with climate change, instead of warming waters, is actually, like you said, changing the composition of the ocean. So for us, we have already a pretty low oxygen level in our waters. And what they've discovered is over the past 60 years, the oxygen levels are getting even more dramatically low, to the point where they could cause stress for animals. And that also what is called our ocean minimum zone is stretching. So it's becoming a larger zone that's more intolerable for animals.
Mm-hmm.
So complications of not just warm water, and then of course, with a lot of animals that make their bodies out of hard things, is that the oceans will also get more acidic, and that makes it hard for things like the gastropods, the snails. So not just temperature down here in the deep. Yeah. Next question from the audience. Yeah.
I was wondering about the lay of the land around these vents. Is it mostly fairly flat, the seabed in the general area for some distance in all directions, fairly flat?
The question is about what's the terrain kind of like down there around the hydrothermal vents? Is it relatively flat?
Mm-hmm. No, it's not. It's those hydrothermal vents, or the boundaries of tectonic plates are, depending if you are in a spreading center, that we call, those are ridges. So it's basically like a chain, underwater chain of mountains, and many hydrothermal vents are found in the valley, in the middle of this ridge. In other places where instead of, those are typically the places where new ocean crust is formed. Then in other places where you have subductions, area where two plates are encountering and one subducts into the other, there is also an elevated terrain, and it's very rocky. So yeah, those are not at all flat places. You have to go several kilometers, maybe tens or 100 kilometers to reach these abyssal plains that make the vast majority of deep sea.
Great audience.
Yeah, lots of questions.
Yeah.
Not all of them easy.
Great presentation.
Thank you all so much for coming. I've not seen any new questions in the chat. Please, if anyone online has anything that I missed, please feel free to bring it up. There was a highlight there for Ocean Networks Canada. They are the ones that have the cabled observatories out. So there's a link to how you can access that information. And also they'll be going out on an expedition this summer. And then also I'll put a plug in for my team. We're going to be going out this summer to some deep sea sites, not hydrothermal vents, but a few others. So yeah.
Take fast answers.
Can I have a last question?
Do we take passengers? It's really competitive, but if you want to put your name in the hat, you talk to me after. We'll talk about the skills we need.
Okay.
Hi.
Oh yeah.
Hello. This is maybe a bit obscure, but what's the relationship between sort of the hot vent, the density and the salinity of that water coming out of those vents? Is there a plume of hot water coming up, or is it too dense? Like what does it look like around the reef, around the deep sea?
Well, all this fluid that is being expelled, as I show in some of the videos, it creates this black smoke, and that is what we call hydrothermal plumes. And so at some point, they became neutrally buoyant, and they can then disperse on the water column for several kilometers. And those are actually important sources of many important minerals that are somehow limiting, for instance, iron and these things. And when these plumes reach the photic zone, these 200 meters depth, these first 100 meters depth, this is the phytoplankton experience blooms because of the iron and the chemicals that is coming from below. So yes, they are sources of chemicals. They create these plumes, and some of them, some of the minerals that are being expelled play important roles in the biogeochemical cycles of the ocean, and iron would be an example of that. So yeah, that's
good. Thank you.
Yeah.
Are there any ownership rights being assigned to these vents outside of the territorial boundaries along countries? For
Right.
example, we hear about areas near the North Pole, where
Uh-huh.
Russia's claiming ownership. So I'm interested in the ownership of the land, even though it's covered by water.
Mhm. So the question is if countries own hydrothermal vents outside the exclusive economic areas. The answer is no. Like the ones that are within countries' boundaries, those yes are managed by countries itself. But the ones that are in international waters, those belong to no one, and then is when the ISA comes into play, and where all these things are being discussed. There are procedures where countries can make claims in certain areas, saying, I want to explore this region or that region for maybe an exploitation in the future. So then the ISA gives permission to do these explorations, having in mind that that could be an industrial activity in the future, but it's not owned. Like some of the hydrothermal vents that I show in the cruise that I did are either claimed by France or by Russia, and we as a scientific team, we were able to dive there and do research. So they cannot limit us to do that, and they cannot start doing what they want, but they can claim to explore these areas for a potential future benefit.
Can I follow up on that
Yeah.
really quick?
Is there any follow-up or any corresponding parallel organization, the one you referred to, that's more focused on advocacy for protecting these areas?
Right.
Because you made it clear to us that there seems to be a priority heading towards the development of these areas for economic reasons. I'm wondering, is there a corresponding organization or a number of organizations that are working to protect them?
Right.
Yeah, so there's a question from the audience that, is there any kind of parallel organization for more like advocacy for protection? And I just wanted to add to Joan's comment before about the ISA. In these areas where there is no country's jurisdiction, they are already grabbing areas and assigning contract sites to mining companies, and then sometimes discussing where the conservation sites within the zones are going to be. So it is already, though they do not belong to anyone, there is already a signing of areas going on. This is largely happening in areas that aren't hydrothermal vents right now. They're going to be targeting these abyssal plains, but there are contract sites already dedicated to different mining companies who have purchased different or have different areas. So it's quite interesting. And then if you can't think of the parallel company, tell us.
Yeah. So as far as I know, well, as I told before, there are some countries that are against deep sea mining. There are some countries that, wants to. In terms of organization, I would say the DOZI. The DOZI is the Deep Ocean Stewardship Initiative. This is a great organization. It's basically an NGO, so non-governmental organization, and it's basically a group of scientists, but also lawyers and also from other disciplines that try to raise awareness of the issues related with the deep sea and the emerging threats in the deep sea. So the DOZI, for instance, go to these meetings to make sure that the science is being exposed. So the representatives of the country can decide. DOZI would never go with the vision of saying, yes, do this, or no, don't do that. DOZI puts the science in front and then let the policymakers, stakeholders to decide. And so it does so in a variety of ways, from doing policy briefs that then you can distribute on important meetings, also going to symposiums and congresses where these things are being debated, but also having a seat at the ISA and being able to ask questions and show evidence here and there before any decision is being taken. So there are some other groups that are doing similar things. For me, I think that in terms of deep sea, the Deep Ocean Stewardship Initiative is probably the one that gather more scientists and lawyers working towards raising awareness, basically. Yeah. Yeah.
Have you found any evidence of plastic pollution in the deep ocean?
Yes. So the question is if we have found evidence of plastic pollution in the deep sea and hydrothermal vents. Yes, in the cruise that we did, that was in the middle of the Atlantic Ridge, and we spot some Coca-Cola cans and then some plastic bags. Not many, it's not something as you can see in shallow waters, but still it's surprising to find things at 2,000, 3,000, 4,000 meters depth. And then very surprisingly, and well, that's kind of a personal experience, but these high, not the ones that I show you in the cruise that we did, but many of the vents that I showed you before in the first part of my presentation, those are vents that have been visited many times by scientists. And so what you find there is what we call pollution related with scientific activities. So scientists also a lot of times leave products there that sometimes if they use submersibles, a lot of times for the buoyancy of these vehicles, they need to release weight. So you see these bags of metal in there or pieces of metal. And yeah, it's not that uncommon that you find this kind of scientific pollution on hydrothermal vents. So yeah, that's something that it's being debated now on how to clean these areas that are, visited several times, and to invest some time in retrieving all these items that shouldn't be there. Yeah.
Mindful of everyone's time. Thank you so much for coming in today. Thank you for the audience online. Everyone's been super engaged and awesome. And thank you to our awesome speaker.
Thank you very much.
Join us next month. I will be here in this room, but our speaker is from afar, so they will be online. But you're welcome to come to this room if you want. If not, feel free to join online. And thank you everyone again.
Thank you. You want me to?
Sure. I can if you want.
Fascinating.